Hi everyone, Dr. J here, and in this video we're going to be discussing stochastic and deterministic models, which is part of our modeling uncertainty series. Now I have a definition for you here. A deterministic model is a single model, Earth model, can be a few, but usually a single Earth model that includes most accurately all physical and spatial relationships at the finest detail computationally possible. So you collect some data and then you build the best possible model that you have that can explain those observations and can be used to forecast or predict. And a good example of one of these types of models is a global circulation model, or GCM. These are climate models. So you can see here an example from Wikipedia. There's a global grid to some resolution. The whole world is gridded. And there are all kinds of physical processes that go into these models. And you can see just some examples here: solar radiation, terrestrial radiation, interactions and feedbacks between glaciers and the oceans and the atmosphere, as well as land. Obviously, temperature, water are moving around in the atmosphere. These very complicated physical processes have to be modeled. And yet, at the output, at the end of the day, what we often are looking at from these models is a single curve, which is a global warming projection, a temperature anomaly. And they can make other predictions as well, but this is really perhaps the most important thing that we look at. And you can see here a number of, half a dozen or a dozen global climate models that have been published in the past. Now, there's all kinds of interactions that go into these models, and one of the problems with building a single deterministic model is you really cannot possibly model all of the processes that are active in the atmosphere, for example. So just this plot shows some more interactions, and these are not necessarily even captured in current state-of-the-art climate models. And there are even more processes that are not shown here, such as interactions of the carbon cycle with plate tectonics and volcanoes and their influence on the carbon cycle. So there's all kinds of different processes that interact in our atmosphere to produce an overall climate change or climate shift, or just the climate in general. And it's very, very difficult to model all of those physical processes at the resolution that we really need to make these kinds of forecasts and prediction. Now, does that mean that those temperature forecasts are wrong or bad? Not necessarily at all, because it all depends, again, on what our objective is. We can identify where we can make simplifications and try to do this. Now, with a large global circulation model like this, obviously there's all kinds of problems that are not even relevant for this class, such as numerical issues in modeling, just the scale of being able to model that kind of a problem, computational complexity, and so on and so forth, unknown feedbacks and interactions. These are all problems, but deterministic models incorporate the best of everything in order to account for as much physics as possible, do the best possible job modeling these systems. But even then, as we've seen, they can still be oversimplified, and they are always uncertain. So as I said, our very simple reservoir storage volume model is an example of a stochastic model where we take into account explicitly uncertainties in the input parameters. And in this case, we're not really modeling any uncertainty in the model itself. We're not taking into account the relationship between stress and porosity, for example. But we're able to produce some uncertainty based on our input parameter. And we don't get just a single answer, but we get a whole suite of simulations that are hopefully encompassing the range of reasonable values that we can expect to find. Now, obviously, once you get to more realistic models, parameters and model complexity very quickly grows. And you can see here an example of reservoir modeling, where you have a number of different parameters and they all have different distributions. And this additional complexity is one reason why stochastic modeling hasn't been used more often than it has. So for example, in groundwater modeling, not as much as it could be and probably should be. Running one groundwater model might be challenging, but running hundreds or thousands of groundwater models, which is what you would need to do to really characterize uncertainty, can be prohibitive. And so this leads us to really the focus of this particular module in this class, and that is to think about what are the uncertainties that are associated with every step of our modeling and forecasting process. We have our observations, we have various types of models, physical models, spatial models. Others are associated with those models, and then eventually we end up with a forecast, and we have to actually make a decision. And what we want is for all of the at each point in this kind of tree diagram, motivated and guided by our final forecast and decision that we need to make. So what's the decision that we have to make? Is it to predict flow volumes? Is it to predict earthquake potential? Because we could quantify a lot of uncertainty, but if those uncertainties are not really relevant for our decision model, or if they don't have an impact on the decision that we make, it doesn't matter. We don't need to quantify those. All right, so let's just quickly walk through this chart, this diagram. So we have raw observations, which are the actual raw values which come from our instruments. So this would be like raw electronic signals from seismic data, or core, you might have measurements of grain size and porosity. And then there are parameters, almost always either unknown or uncertain, at least in three or four dimensions. So for example, stress in the Earth's crust. We might measure stress at the Earth's crust, in the Earth's crust at a borehole, but that's at one particular location and one particular time. How is stress changing in the crust? How is it changed during the time when your layers were being deposited, your sedimentary layers and so forth? These things have to be estimated, and they are, as a result, uncertain. Then you have your physical model, which is, in some cases, the correct physics is uncertain. So as I said, with these global climate or global circulation models, we oftentimes are approximating the true physics, which is very fine-grained and high resolution, with some aggregate physics, which has been gridded up at a global scale and it has to be coarse. And so there's uncertainty that's associated there. We almost never have measurements anywhere, and so we have these spatial models where we try to characterize spatial variations and spatial uncertainty, but those are also uncertain because we don't have measurements everywhere. And then finally, to come back to this point, we have to make a decision. There's a decision that needs to be made, which is driving all of this uncertainty modeling, which is driving all the modeling to begin with. And we need to try to focus on what's the decision. If you're in scientific research, there might not be a specific decision that has to be made, but there might be a hypothesis or a question that you're trying to answer. What is the earthquake potential of a particular fault system? What's the total petroleum stored in this reservoir, and how much of it is producible? What's the temperature change, global temperature change for the next 50 years? What is the effect of producing water at this location and at this rate on the groundwater storage system? So these are all decision questions, and these have to motivate our work and our efforts to understand uncertainty at each one of these boxes. And here's just an example where, let's say that we're trying to build a reservoir flow model. So we might have all these different things. We'll have our data sets, whether that's seismic data or boreholes, logging measurements, and so forth. We might have gravity or magnetics. We'll build some type of spatial model for the geology. We'll have physical parameters such as porosity and permeability. There'll be a physical model such as flow, and those are all feeding into each other to lead to this final forecast and decision making. So whatever that looks like, whether it's to clean up or not to clean up a pollution site or whatever it is, that's where all of these things are leading to. All right, so with that, I'll wrap up and see you in the next video.